Hello everyone, my name is David, and for today this is going to be the first videos about the Solow growth model. And in this particular episode, we're just going to go over what is the Solow growth model, what's it for, and what are the basic assumptions that underpin it. So the Solow growth model is basically just a model that we use in order to predict what consumption, output, and capital levels are going to be in the long run. All right? So let's start with the assumptions that underpin it. The first assumption is that we have a Cobb-Douglas utility function. And it's going to be an aggregate production function that's going to look something like output in the current time period is going to equal technology times capital to the alpha in the current time period times labor to the 1 minus alpha in the current time period. What we're going to do from there is turn it into a per capita function. And so, to do that, we just divide both sides by L. Right? And this will be rewritten as little y, output per capita, is equal to technology times k, little k, to be exact, to represent capital per capita to the alpha. And so that's going to be an important function. Assumption number 2 is that we have essentially an aggregate savings function that looks as follows. Investment in the current time period is equal to capital in the future minus 1 minus the depreciation rate of capital times capital today. Okay? And the reason this is useful is because we can rewrite this equation to solve for what capital in the future is going to be. So we just subtract 1 minus dkt to both sides, and we'll find that capital in the future is equal to investment today plus 1 minus the depreciation of capital today. We then turn this into a per capita function, like we do for all of our functions. And so we can rewrite this as, divide both sides by L. Now this particular equation is going to require a little bit more mathematical manipulation, right? Because if you notice, on the left side of the equation, well, this will just become little I, so investment per capita. And this part just becomes 1 minus d to the little k, capital per capita. But notice we have an incongruity here. We've got capital in the future divided by labor today. So how can we essentially manipulate this so that we get it in a form that is helpful to us? Well, this right here is equivalent to capital in the future over labor in the future times labor in the future over labor today. It's the same thing, right? After all, if we did multiply these would cancel out and we would have capital in the future over capital today. But by rewriting the equation like this, we can now essentially make it usable for our purposes. So this right here is the equivalent of little capital in the future, right? Times, well, L, labor in the future, is just 1 plus the growth rate of the population times L in the current time period. So that's going to be times 1 plus N. We'll use N to signify the population growth rate of LT over LT. And so these can cancel themselves out, and we'll be left with capital per capita in the future is equal to this investment today plus 1 minus the depreciation of capital per capita today over 1 plus the growth rate of capital. And so this right here is another important function we're going to be using later. All right, what's our third assumption? Our third assumption is there is no government spending nor exports or imports. So this is a closed economy. What does this mean? Well, in our typical GDP function, we have output is equal to consumption plus investment plus government spending plus net exports. Well, this is going to be equal to 0, so it disappears. This is going to be equal to 0, so we're just going to be left with this. And from here, we can alter this equation by subtracting consumption on both sides. And what that'll tell us is that investment today is equal to our total output minus our consumption, which makes sense. Whatever we don't consume is essentially our savings, and in a closed economy, this, our savings, must equal our investment. So that's going to be the next thing. Investment in the current time period is equal to savings in the current time period. And once again, we're going to turn it into a per capita function, so divide both sides by L. And so we'll have investment per capita is just equal to savings per capita. Right there. And then our last assumption. What is our last assumption? Our last assumption is essentially savings is going to be a constant fraction of output. Little s, savings per capita, is just going to be some savings rate that we will call sigma times our total output. Right. By extension, then, if savings is sigma times output, well, consumption, which is the opposite of savings, should be, by extension, consumption should be 1 minus sigma times output per capita. And so that's another important function that we're going to be using to solve problems that involve the Solow growth model. To put all of this information together, where are we going to start? We're going to start with this function right here. Because remember that the point of the Solow growth model is to be able to predict capital in the future, which will in turn let us predict output and in turn consumption in the future. So, to put it all together, we begin with our capital in the future function, kt plus 1, is equal to investment today plus 1 minus the depreciation rate of capital today, all of that over 1 plus n. This is our function, and we know that investment per capita is the same thing as savings per capita, and we know that savings per capita is equal to sigma times our output. So we're going to substitute that in. All right. At the same time, we also know that output can be described by this function right here. Output is equal to ak to the alpha. So once again, let's substitute that in and rewrite this as sigma times a k to the alpha plus 1 minus d kt over 1 plus n. All right. And what this right here is, this is all equal to kt plus 1. And this right here is our law of motion of capital. And this equation is the important one for helping us find output, consumption, and capital in the future. So these are the basic assumptions of the Solow growth model. From these assumptions, we were able to create equations that then helped us create this, the law of motion of capital. To see future exercises to know why is this useful, where would we use it, tune into the next video. And if you have any other questions, talk to your professor or come visit us at the ASU Tutoring Center. Thank you.